Hello and welcome to the Unit 4 podcast on Section 10.1. I'm Mr. Sakaguchi,
And I'm Mr. Lin.
and today we'll be discussing chemical reactions and chemical equations. Chemical reactions are, when bonds are broken and reformed into new products. Evidence or proof that a reaction has taken place is usually observational, so things like changes in temperature, color changes, smells, gas bubbles, appearance of a solid are all indications that a chemical reaction has taken place.
So this is like the ooh-ah stuff that you actually see, and this is what led to the more discovery of chemistry in the first place.
So don't confuse these with physical changes, okay? And hopefully you'll be able to tell the difference. Representing chemical reactions, there are reactants. These are what we start with, and products are things we end with. In chemical reactions, we often use symbols to help us indicate progress of reactions, as well as to separate reactants and products.
Yeah, since science is all about observation, we need the symbols to help write down what's going on or what has happened and what's been observed, so that way other scientists can read it. So on the right-hand side is a table of the different symbols that you're going to run into. Okay, so a plus sign, the arrow is the reaction from reactant to product, solid, liquid, gas states, and the bottom one, water solution, means stuff that's dissolved inside.
And the AQ is short for aqueous, which is dissolved in water.
Right.
There are word equations as well. These are statements to indicate reactants and products of reactions. Sometimes chemical reactions are written like this, where iron, which is solid, plus chlorine gas yields or gives off iron 3 chloride that is solid. And then you can also use the word equation or as a sentence.
Right. So again, here's the symbols for it, and like I said, that's from the observations, and you can write that down. And now that you read it, you can understand what it means and what other scientists observe as well.
So it's a way to move away from like common names to something that's a little bit more formal, and also it prevents us from kind of rediscovering the same things over and over again and not knowing that they're the same because different people name them different things. Skeleton equations are basically like a word equation, but we use chemical formulas instead of names. What's also important to note that skeleton equations are not balanced, and we'll talk a little bit more about what balancing means in a little bit.
The general structure of a skeletal equation is it just tells you what compounds are reacting and what products are produced. So the example at the bottom, you just got iron, and you've got solid iron, and you've got gaseous chlorine gas, and then you've got your solid iron chloride at the end. And also notice that this 3 here, we talked about in the previous PowerPoint about how that 3 represents that +3 charge of iron. That doesn't show up in our chemical formula. Just a quick rundown on that.
And again, notice the difference between a skeleton equation, which is not balanced, versus a balanced equation. The reason why we balance chemical equations is to satisfy the law of conservation of mass. Basically, this is something that states that matter is neither created nor destroyed. And the idea behind this is that if I have a certain number of atoms on one side, I better have the same amount on the other side. So in other words, we're taking into account all the different elements and their amounts on each side of the arrow.
Right. So since matter can't be created or destroyed, everything that you put into a chemical reaction, you will get the same amount of material on the outside, even though you just rearrange it. So if you had like a jar filled with, in this case, methane gas and oxygen, and you lit it on fire inside, and you had this reaction running on top of a scale before you lit it on fire, and then after you lit it on fire, that scale would measure the same amount, the same weight. Nothing would change. And that's why we have our balanced equations.
The way we'll balance is by putting numbers in front of the chemical substances on either side of the arrow. And we'll talk more about what these mean. These are known as coefficients, and basically they tell us how many of each. What results, if you can look at this example here on the bottom, it results in equal amounts on both sides. So we have 1 carbon here, 1 carbon here, 4 hydrogens here. 2 times 2 is 4 hydrogens here. This 2 multiplies all the way through. We also have 2 times 2 is 4 oxygens on the left-hand side. 2 plus, remember this 2 multiplies to this, because it means 2 waters, not just 2 H2s. We always end up with 4 on both sides. And we'll talk in a moment about how you actually do this in a systematic way.
Right.
And I know a lot of you probably have done this in middle school, so hopefully it'll be a refresher to you. The steps of balancing chemical equations. Well, the first thing you need to have is you need to have the correct skeleton equation. Once you have that, you can take into account the amount of each element for the reactants and do the same thing for the products. And then what you want to do is you want to place coefficients in front of the reactant and product compounds or elements as necessary to end up with equal amounts of each type of atom on both sides of the arrow. You also want to make sure you write your coefficients in the lowest possible ratio. So in other words, if you have 2, 2, 2, a bunch
All
of 2's
across, right.
all across, that reduces to 1.
Right.
Also check your work, because since this is balancing, if you don't have the same amounts on both sides, it can't possibly be correct.
Right.
So hopefully these are things you never miss.
One thing to keep in mind is that the first step about knowing what the skeleton equation is, this will go back to the chapters 8 and 9, where you had to know the process of going from the name of a chemical compound to writing out the formula. So brush up on that if you felt a little shaky about it previously, because it's coming back here.
Here's an example of balancing. So in this case, we gave you the skeleton equation. You're not always going to get it, but sometimes you'll start with this. So in the second step, we have 1 sodium on the left-hand side, 1 oxygen, 1 hydrogen, 1 calcium, and 2 bromines. Okay. On the right-hand side, we have 1 calcium, 1 calcium, 2 oxygens, 2 H's, 1 bromine, and 1 sodium.
Thing to keep in mind, remember these are just symbols telling you what state the matter is in. You don't actually shift those down into writing out the reactant as products. So don't let that throw you. It's just for the skeleton equation itself. After which you have figured out the numbers or amount of each element in reactant and product, you can start multiplying certain compounds to make sure that you have the same amount of both reactant and product for each element. Now, in this first example, you might notice that you have 1 oxygen for the reactant, but 2 oxygen in the product. Now, to get to that, you're going to have to do some multiplying. So to get from 1 to 2, you're going to have to multiply your reactant by 2. To do that, you have to multiply by the whole package. So you stick a 2 in front of the sodium hydroxide, and that affects that oxygen. So now you've got 2 oxygen on the left and 2 oxygen on the right. But this 2 affects the whole thing, so that means you also now have 2 sodium and 2 hydrogen on the reactant side. On the product side, that gives you your 2 hydrogen there. But now what would have been your sodium is out of balance because you only had 1 before. So this also has to be multiplied. And you keep going back and forth. So now you have 2 sodium and 2 bromine. Come back over here. Oh, you already have 2 bromine, so you're good. So now you have a ratio of 2 to 1 to 1 to 2, as shown from the balanced reaction.
A couple things to note is that you're only allowed to put coefficients in front of compounds. You're not allowed to change the formula. You're not allowed to put this 2 in between,
Right,
or anything like that. You have to leave the formulas as is, and you're only allowed to put them in front. And remember, whatever's in front applies to the whole thing. So when I put a 2 in front of here, what that basically means is that I actually have 2 formula units of sodium hydroxide, not just 2 NAs, 2 O's, 2 H's. We break it down for the purposes of balancing only, but don't think that's
you're
what
breaking
really
it all
right.
apart. Right.
Okay. If we go back, and now that we have the 2 to 1 to 1 to 2 ratio, we can go back and double check our work. So we have 2 sodiums and 2 sodiums. A lot of times with the polyatomic ions, a lot of the times they're not going to break apart. So instead of counting O's and H's individually, sometimes it's easier to count the polyatomic ion as one unit. So now what I've done is, instead of doing O's and H's separately, I've made OH hydroxide, one of the polyatomic ions, one thing. So now we have two OHs. Well, we also have two OHs on that side. So even though I got two OHs by putting a coefficient in front versus two that was part of the formula in parentheses, it still adds up to the same thing.
Right.
One calcium, two bromines, and then remember this 2 applies to two bromines as well. And now this is for sure our final answer.
Right.
And that is it.